Okay, it's time at 7:05. Let's go. So today, let me open the slides on the slide. Today we are discussing about the transient heat conduction, and the most basic of the transient heat conduction is the lumped capacity system. In the lumped capacity system, we assume that okay, so let me draw. Let's say this is a ball, okay, and at the center, the temperature is, let's say, 100 degrees Celsius. Outside, T infinity is, say, 10 degrees Celsius. Although such a temperature is not there in Singapore, but some places, at least the place where I come from, temperature goes even below 10. So, two things are going to happen. One is that there is going to be convection, convection, which will happen. And along with that, there will be some conduction happening as well. So this is conduction because the center is going to be heated and very quickly the surface is going to uh, the surface temperature is going to reduce because of convection, and hence the center is going to provide the heat. Okay, take my heat. So two things are happening: one is conduction, one is convection. Now, in what case can we ignore the conduction? Let's say if we have conduction is happening super fast. Let's say we have a copper ball, okay? So conduction is going to happen very, very quickly. Versus, not versus, I think I'm going to say okay. And the convection is super slow. Okay. If this is the case, then we can ignore the temperature difference which is going to arise between the T center and T surface. What I'm trying to say is that you can say that the whole ball is almost going to be at the same temperature, and the whole ball itself as a lumped capacity model is going to lose heat, and that heat is going to go away in the atmosphere. Now, how do we quantify it? Usually, such things happen when there is annealing happening. For example, if you have a very heated metal ball and you directly dip it inside the water. In that case, because the temperature difference is too much, this is, let's say, 1,000 degrees Celsius, and water is at 20 degrees Celsius. In such cases, usually such things happen. When, uh, okay, so let's discuss this thing mathematically. Mm, okay. So mathematically, we can say that uh, the resistance for convection is much more than the resistance for conduction. Or in other way, we can say that the Q dot convection is much less compared to Q dot conduction. Using this equation, what is R convection? It is HA delta T. And what is Q R conduction? It is K A over L most likely, if not the reciprocal of it. If the area increases L over K, now this, okay. the reciprocal of this, which is L over Ka, because if length increases, the conductive resistance also increases. So we are essentially saying that HA delta T should be very much greater than L over Ka times delta T, right? You can cancel out the delta T term. And even the area term. Am I making a mistake? Seems like I'm making a mistake. L, yes. Uh, it is so very greater than Ka over L times delta T. My internet connection is unstable. Why is it so? Deal with it a bit later. So mathematically, what we are going to do is we will, so we can say over L, and it brings us to a term which is H L over K is very, very greater than 1. Let me check if someone has joined. Okay, we have one person. Thank you. Uh, so essentially, HL over K is very less than 1. Usually, the way it is defined as Biot number, which is HLC over K, is very, very less than 1. Or in quantifiable terms, people talk about the Biot number is if it is less than or equal to 0.1, then we can treat the system as a lumped capacity model. This is all what you have to remember. That the Biot number, which is HLC over K. Why am I writing LC and not L? Because LC is the characteristic length. Because it is not always a plain ball, right? It can be a cuboid through which uh, lumped heat capacity model is acting. In such case, how do you define the length? It cannot be just the breadth. It cannot be just the length or the height, right? So there is something called characteristic length. What is it? We are going to discuss. Now the characteristic length. Okay. Some characteristic length is LC, which is B over AS. B is the volume and AS is the surface area of the system. So you can derive it for anything. For example, for a plain ball, these are the three cases which have been taken in the lecture slides. So for a plain ball, it is LC equals L over 2. For a long cylinder, it is LC equals R over 2. R is the radius. And for LC equals R over 3 for a sphere. It's very easy to calculate. For example, for a sphere, what is the volume? The volume is, if I'm not making a mistake, 4 by 3 pi r cube. And what is the surface area? It is 2 pi r square and 2 pi, I think 4 pi r square, right? So, which is r over 3. This is how you calculate the characteristic length. Now, There are a few examples which I see in the lecture slides. Okay, now the main equation of the lump capacity model. So lump capacity model equation. Okay. Uh, there are two things which are happening. I can go through a derivation as well, but I think I'm going to go directly to the final equation because derivation is going to take a lot of time. Uh, you can, okay, let me first write down the equation. T minus T infinity over T minus T infinity is equal to minus H AS over rho V Cp dt. This is the equation which comes by when you equate the heat transfer, which is happening inside the body in a small time dt. You are equating that with the increase in the energy of the body. You can say that H times AS times T minus T transfer into the body in a small time dt, in a small time dt. You're equating it with a small increase in the energy of the body. What is the energy of the body? It is mCp delta T. But it is in a small time dt, so it's going to be d capital T. And d capital T can also be written as d T infinity minus T, right? So from this, if you put T infinity minus T as some constant K and you do the math, you're going to get to this equation. From this, we define a variable. It is called uh, Biot number, which is uh, not the Biot number, time constant, which is B is equal to H times AS over rho V Cp. If we define a constant B like this, the equation which we are going to get is uh, ln of t at any time t minus t infinity over t initial minus t infinity is equal to minus uh, HAS over rho B Cp times T. And if you want to uh, raise everything to the power of E, you're going to get T minus T infinity over Ti minus T infinity, which is this whole thing is B, right? This is B. So we can say e to the power minus bt. It's a very simple equation. Here, v is the time constant, t is the time, T infinity is the outside temperature. Outside temperature. This is initial temperature of lumped mass. And what is TT? TT is the temperature of lumped mass at any time t. Okay. So if let's take an example and it's going to be a little more clear. Okay. So if we have a ball and in this ball, let's say it is at the temperature of 100 degrees Celsius and the outside temperature is say 20 degrees Celsius. In that case, this ball is going to lose heat. So after, let's say, at t is equal to 0, this is the case, right? But what is going to happen after 100 seconds? So ball is going to come at a temperature of, let's say, 80 degrees Celsius. So 80 here is t as a function of t. What is 100 seconds? It is t, right? And What is T infinity? It is 20 degrees Celsius. What else do we have in the equation? And I think that's it. P we can calculate depending on the dimensions of the ball and CP of the ball, like those things, and the volume as well. So that is all what you need to remember in the lump capacity model systems. Um, this is the only equation which we are going to use. After that, we have, okay, there is diameter which is generally less than 1 mm. So you'll have to go through the slides once, and then only, like, without going through the slides, it's going to be difficult to like explain this. But as of now, just in case the question mentions the gauge number of the thermocouple, we can know how much is the diameter of the wire of the thermocouple using this table on slide 16. Oh, I think my content is not being shared. Okay, it has been shared. Right. So using this table, we are going to understand, like, we can use this table to know the diameter of the thermocouple. Now coming to temperature measurement by thermocouples. Okay, this is the question. Okay, I think today's class is going to be like quite short because we are done with the theory. And in previous two sessions, we covered two lectures contents. So even the contents took a lot of time, and then I had to also go through the questions. But like this time, I'm just going to, like, the content is done. So let's jump quickly to the questions, and I think we'll be done for this session in less than, I think, total 50 minutes. So before, I think, before 8 p.m., I'll try and finish. So I think I have shared like three problems with all of you. Um, let's open up the problems. Okay. This is one problem. It states that the temperature of a gas stream is to be measured by a thermocouple, uh, whose junction can be approximated as 1.2 mm diameter sphere. Okay. So uh, we have the diameter is 1.2 mm. And then properties are given. So K is 35, density is 8500, CP of that thermocouple is 320 joule per kg degree Celsius. And the heat transfer coefficient H is also given. So everything is there. H is 65 watt per meter square degree Celsius. Determine how long it will take for the thermocouple to read 99% of the initial temperature difference. Okay. Uh, what the question is asking is us is that, okay, I think you guys can spend like 1 minute understanding and thinking about how to approach this problem. After that, I'm going to solve it with you. One big issue with the lumped capacity system models is that, because right now we know that we are discussing the lumped capacity model, so we will directly go to thinking about uh, how to first calculate the buyout number and check whether the system is applicable, the lump capacity model is applicable to the system or not. But in the question paper, the question won't say that, okay, you have to apply the lump capacity model here. So you'll have to think a bit about, based on the, like, for example, the diameter of the sphere and how much is the heat transfer coefficient, how much is the thermal conductivity. You'll have to think a bit whether this question is from the lump capacity model or not. That's the difficult task. So you'll have to be careful right now because we are discussing the lump capacity model. So it's like very easy. We know that we have to apply that equation. But in the question paper, it's going to be difficult because there are going to be different uh, questions from different sections. Okay, so let's begin. Uh, First of all, because now we said that we are applying the lump capacity model, so we'll do that. First of all, what has to be calculated? First of all, we want to check whether the lump capacity model is applicable or not. For that, what do we have to calculate? We have to calculate the buyout number. This is the first thing which you calculate and see whether it is less than or equal to 0.1. Now, what is the equation for the buyout number? It is H times LC over K. What is H? We know. What is K? We know. What is LC? We don't know LC. So LC is the characteristic length, which is V over AS, and it is a sphere. So R over 3, because we discussed why volume over the area of a sphere is R over 3, uh, which is the diameter over 6, which is 0.0012 meters over 6, which is 0.0002 meters. I like to keep things in the SI units because that way it's um, very helpful for me. I mean, I'm less prone to making mistakes. Um, Now let's calculate the buyout number very, very quickly. So the buyout number is H. What is H? H is 65. What is LC? It is 0.0002. What is K? K is 35. How do we calculate? Let, can someone do the calculation for me? Meanwhile, I'll also do 65. Hmm. So, okay, I'm getting almost 0.004. 0.0004, almost this value. I mean, something 3714, but you can approximately say this. And it is surely very, very less than. So the buyout number is very, very, very less than 0.1. So the lump capacity model is applicable. Lump capacity model is applicable, right? Now, once we know that the lump capacity model is applicable, how are we going to, like, the problem is very, very simple. The problem says the way they have expressed the problem is a bit tricky because they say determine how long will it take for the thermocouple to reach 99% of the initial temperature difference. Initial temperature. Thermocouple measures the temperature difference always. So the initial temperature difference, uh, delta T initial is Ti minus T infinity. And what is the final temperature difference? Delta T final is T at some time T minus T infinity. What they are asking us to find is, what is this T? Let's call it T naught. They're saying uh, when uh, delta um, when T at any time T minus T infinity over Ti minus T infinity is 0.01. You'll have to think a bit about why 99% of the initial temperature difference gives us this equation. They are saying that T uh, 99% of the initial temperature difference. So Ti minus T infinity times 99 over 100, and you subtract it from 1, is going to give you T minus T infinity. This is how the language translates, and this equation is going to bring you to this equation. Tt minus T infinity over Ti minus T infinity 0.01. If you ponder a bit about, like, on this, the way they have expressed this language, you're going to arrive at this equation directly. Now, okay, but we also know that uh, let me see. But we also know that Tt minus T infinity over Ti minus T infinity. This is also e to the power minus Pt, right? Because we have the lump capacity model applicable. So we can say 0.01 is e to the power minus B times T. Now what is B? B is H times As over rho V Cp. You can say it is H times H over rho V, not V, rho Cp LC, because V over A is the LC, right? We'll have to calculate LC, I think. So LC we already have. LC is 0.0002, right? So I think we have B directly. B is H, which is 65 over, what is the density? 8500 times, what is CP? CP is 320, and it is in SI units. What is LC? LC is 0.0002. The answer which I have here is B is 0.1195 second inverse. This is the value of B. You can calculate the T naught, right? It's very simple. So 0.01 is e to the power minus 0.1195 times T naught. From this, you're going to arrive at T naught is 38.5 seconds. Is the final answer. Simple, right? Because here we knew that we have to apply the lambda capacity model. That's why we directly went on to calculate the Biot number. For the Biot number, we had to calculate the characteristic lengths. We calculated that. Now, the language was a bit confusing when they said that the thermocouple determine the how long will it take for the thermocouple to reach 99% of the initial temperature difference. But from that, we infer that what they are trying to say is this equation. From this, the calculation was very easy. Directly the e to the power minus b t naught, because the last model was apt. And from this, we calculated t naught using some equations. Right? Let's move to the next problem. Screen is lagging a bit. Never mind. Okay, the recording hasn't stopped, so it's okay. I'll have to share my screen again. One more. Yes. So hopefully my screen is visible again. And okay, let's move on to the next problem. The second problem which we've got is 4.23. So let's take a screenshot and then put it on the screen directly. This is the next problem which we have 4.23. Carbon steel walls of density 7833, thermal conductivity. Okay, let's write down while we are reading the problem. So density is 7833. Thermal conductivity is 54. CP is 0.465 and alpha is 1.474 times 10 to the power minus 6. Um, Carbon steel balls, careful in terms of how my net is functioning. There is another there is another friend of mine who is taking the PTP sessions, and he just texted me that Lola Chunia. That means nobody came for his session today because I think you guys had the uh, CA1 today, so maybe many of you are taking rest or something. That's what I'm gonna guess. So density, thermal conductivity, CP alpha, carbon steel balls, and they have a diameter. Okay, so D is 8 mm, 0.008 meters. They are undergoing annealing by heating them first to 900 degrees Celsius in a furnace and then allowing them to cool slowly to 100 degrees Celsius in ambient air at 35 degrees Celsius. So the question is giving us a lot of info directly, which is what is TI? TI is 900 degrees Celsius. What is T final? T final is, or we can even say T as a function of T, which is the final time. It is 100 degrees Celsius. And the T infinity, which is the ambient air, is 35 degrees Celsius. If the average okay, we have H as well. So we have everything. This is like a very, very straightforward problem. 75 watt over meter square degree Celsius. We have everything. Determine how long the annealing process will take. First of all, let's calculate the uh, so directly, let's first of all check whether the lump capacity model is applicable here or not. So we have to calculate the Biot number again. What is the Biot number? Biot number is HLC over K. What is LC? LC is V over AS, which is, again, this is a sphere, so R over 3, which is 0.004 over 3, which is 0.0013. This is what I'm going to take, meters. So plugging this into here, we'll say 75 times 0.0013 over what is K case 54. The answer which I have here for the Biot number is 0.0018. Is it less than 0.1? Very much less than 0.1, right? So again, lumped capacity model is applicable, right? So as of now, we have just proven that the lump capacity model is applicable. Now, um, we directly have to apply the lump capacity model equation, right? So we'll directly say, let me extend this line to even further, because we will end this question within this area. T as a function of t minus t infinity over ti minus t infinity is e to the power minus bt, right? I think we have almost everything. Okay, do we have t as a function of t? Yes, we have. It is 100 degrees Celsius. Minus what is T infinity? 35 degrees Celsius. Over what is Ti? Ti is 900 degrees Celsius and minus T infinity, which is 35 degrees Celsius. All this is equal to e to the power minus b times t. What is b? How do we calculate b? Biot number is, no, this is the time constant, which is h over rho cp lc, right? Which is 75 over, I just got the confirmation. Never mind. Sorry, I get a bit distracted sometimes in between because like my internet was not working and I'm using my mobile data, so I have to look at my phone again and again, and that's what causes the distraction. Sorry about that. 75 over density, which is, do we have density? Yes, 7833. What is CP? CP is 0.465. What is LC? Oh, times 1000. Please note the unit. Okay. I made a mistake here. I did not use the SI units. Because I got a hint because I was thinking, why is carbon steel ball having a like CP of 0.465? It doesn't make sense. So that's why I again look back at the question and it said CP is 0.465 kilojoules per kg degree Celsius. And that's what brought me to this multiplying it by 1000. What is LC? LC 0.0018. If you're going to calculate, you'll get the value of B as, what do I have here? Um, okay, I have 0.01584. What is the unit of the time constant? Not the Biot number. This is the time constant, small b. You see this, the LHS has no unit here, right? So here also it is supposed to have no units, and b is getting multiplied by t. So the unit, it needs to be dimensionless because it is being raised to the power of e. So t is second, so b is going to be second inverse, right? So second inverse, the time constant. Usually the time constants have this unit only, second inverse or like minute inverse, depending on in which area we apply. Um, is it less than, okay, this is the time constant, not the Biot number. So we don't have to check whether it is less than 0.1. That we already did for the Biot number. Now just plugging in the equation, the value of b, 100 minus 35 over 900 minus 35 is e to the power minus 0.01584 times t. From this, we can very simply calculate t as 163. This is the answer which I got. What's the unit? Seconds. So it is going to take almost like 3 minutes to for the balls to get annealed and finally reach a temperature of 35 degrees Celsius. 100 degrees Celsius. Now the problem has a part B. Part B says that determine how long the annealing process will take. Okay, this is done. If 2,400 balls are to be annealed per hour, determine the total rate of heat transfer from the balls to the ambient air. Uh, okay, so we have number of balls as 2,500. This is simple math problem. This is not something related to physics of melting or heat transfer. 2,500 balls per hour. Per hour. Okay. Determine the total rate of heat transfer from the ball to the ambient air. So Let's calculate the heat transfer for one ball. Okay. So Q for one ball is mCp delta T, right? Q for one ball is mCp delta T, which is how do we calculate M? I think. Hmm. So you'll have to do a bit of math, and then because there is like a lot of calculations, but every calculation is very simple. So for example, what is M? M is density times volume, right? We have the density. Yes, we have the density, which is 7833. What is the volume? Pi d cube over 6, right? So the value which I have for the mass is 0.0021 kg, which is mass of one ball. So we have 0.0021. What is Cp? We have Cp, right? 465. Now this is it in SI units. What is delta T? Change in temperature. 900 minus 100. So from this, you're going to get, uh, wait, this is not 900 minus 100. It is T final minus T initial, right? So it is 100 minus 900. So from this, you're going to get Q as minus 781. Everything was in SI units. So Q is also going to be in SI units, which is joules. Okay. Uh, Now, let's say we have, they're saying that we have 25,000 balls per hour, right? So total heat transfer, which is uh, total heat transfer by all balls in 1 hour. How much is it? Minus 781 times 2500, which is uh, something. So how much is it in seconds? Uh, in 1 hour is this. In 1 second, it's going to be minus 781 times 2500 over 60 times 60, right? Very simple math. We're converting it to minute and then to seconds. So from this, we will get total Q dot of 2500 balls is minus 543 joules per second, right? Joules per second, which is watt. So minus 543 watts is the final answer. Why did we calculate it in seconds? Because usually that is the SI unit and we wanted to get the final answer in watts. Ideally, we could have written, okay, it is, um, we can simply write this is minus 781 times 2500 joules over hour, but this doesn't look like a very good unit, right? That's why this is the correct way of like ending the answer. Watt, which is a standard unit. We are done with two problems, and I think I have one more. Yes, I have one more, and it's 7:49. So I think I'm spot on in terms of time. I'll hopefully end before it. Uh, 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 so pasting the question here. This question says an ordinary egg can be approximated as a 5.5 centimeter. This whole section of week 5, which is lump capacity model, is very simple. I mean, I would say it is the most simplest uh, topic in this whole module of heat transfer, at least for me. So an ordinary egg can be approximated as a 5.5 centimeter diameter sphere whose properties are roughly K, we have alpha, and the egg is initially at a uniform. I don't know why do we have alpha here, because there was no need of alpha in the previous question as well. The egg is initially at the uniform temperature of 8 degrees Celsius and is dropped into boiling water at 97 degrees Celsius. Taking the convection heat transfer coefficient to be H equals 1400, determine how long will it take for the center of the egg to reach 70 degrees Celsius. Think of it. Again, I think um, it's a very direct problem, right? Okay, let's begin. How do we begin the lump capacity model problems? Very simple. We first of all calculate LC, and then we calculate the Biot number, and then we check if the Biot number is less than zero point 0.1. Or we can even directly go to the final equation of the lump capacity model. But let's first check the Biot number. Okay. So LC is V over AS, which is spares. So R over 3, which is 0.055 over 6. Okay. So what is Biot number? Biot number is H times LC over K, which is, what is H? Do we have H? It's 1400. What is LC? 0.055 over 6. What is K? K is 0.6. What is the Biot number which we are going to get from this? If someone can give me the final answer. 64.2. 64.2 is the Biot number. Is it less than 0.1? Less than or equal to 0.1? No, right? So no, it's not less than 0.1. So lump capacity model is not applicable. So this is where the questions are going to trick you. This is I purposefully chose this question because you might have simply proceeded directly to the lump capacity model equation, but it won't make sense because the Biot number itself is not less than 0.1. It's so high. You can even think from this way that the heat transfer coefficient is so high and the thermal conductivity is so low. Okay. So most likely the convection is so high and the conduction is so slow that the lump capacity model is very doubtful, because in lump capacity model, what happens is the heat transfer coefficient is very less and the thermal conductivity is very high. You can remember from the example of copper balls. Copper balls usually have lump capacity models applicable on them because they have very high thermal conductivity. Now, when LCM is not applicable, how do you get to the final answer to this problem? We are stuck, right? Or are we? No, we are not. Because we solved these kind of problems previously. Come on. It's This is the egg, okay? This is the center. It is at temperature T I T C, okay? There is a conductive resistance, and this is Ts. And there is a convective resistance, and this is T infinity. So very simple problem, right? You can use the resistance series analogy and get to the final answer. I'm not solving it directly. You can get to the final answer. I usually leave the last problem, but I think this one I brought almost till like 70-80%. These kind of problems we've solved previously in, I think, the first session, not the first session, I think the second session. So you can arrive at the final answer. If someone is going to put that in the Teams chat, I'm going to respond whether that answer is correct or not. Let's see if you guys actually do it or I'm wasting my time here. So we'll leave it here, and I guess it's time to stop the session. And luckily, we have recorded everything in time today. So thank you for joining, and see you guys later next week. Bye bye.